Our journey begins in ancient Greece, long before telescopes or particle accelerators. People gazed at the same sky we see today, sun, moon, stars, and started asking, why do these things move? What are they made of? Early thinkers like Thales, Anaximander, and Pythagoras sought natural explanations for the cosmos, moving away from myth. The Greeks believed the universe was ordered and knowable, a radical idea that set the foundation for science. Their real gift was rational inquiry, and the belief that the universe could be understood. This idea, that the universe is knowable, remains at the heart of physics today. For centuries, Aristotle's physics ruled, but the Renaissance sparked a new approach: experimentation. Galileo challenged old ideas, revealing a more complex universe. Enter Isaac Newton, the rock star of physics. Inspired by a falling apple, Newton realized gravity's reach extended from apples to the moon. He invented calculus, and his laws described everything from thrown balls to planets. The universe became a giant, predictable machine, a clockwork cosmos. But some mysteries, like light and electricity, hinted at deeper questions. The next revolution was just around the corner. Newton's laws explained gravity and motion, but electricity and magnetism remained mysterious. Static electricity and magnetism were once parlor tricks, not part of the grand universe. In the 1800s, Michael Faraday connected electricity and magnetism through experiments, discovering electromagnetic induction, the principle behind electric generators. Faraday introduced the concept of fields and visible lines of force filling space. James Clerk Maxwell unified these discoveries into 4 elegant equations, showing electricity and magnetism are 2 sides of the same coin. This was the second great unification in physics. Maxwell's equations revealed that light itself is an electromagnetic wave, a vibration of electric and magnetic fields. Suddenly, optics, electricity, and magnetism were all connected. The universe was more complex than Newton's clockwork. Maxwell's work set the stage for a new revolution, but his equations contained a surprise. The speed of light is always the same. This constant would soon challenge everything physicists thought they knew. The next leap would change our understanding of space and time. Physics was about to enter the age of relativity. By the late 1800s, physics seemed complete. Newton for gravity, Maxwell for electromagnetism. But Maxwell's equations said the speed of light is constant, clashing with Newton's relativity of motion. Enter Albert Einstein, a young patent clerk with a bold idea. What if the speed of light is truly constant for everyone? His special relativity showed that space and time themselves must be flexible. Time slows down, lengths contract, and space and time merge into space-time. But what about gravity? Newton's gravity acted instantly, but relativity said nothing can travel faster than light. After a decade, Einstein unveiled general relativity. Gravity isn't a force, but the curvature of space-time caused by mass and energy. Picture a bowling ball on a trampoline, mass bends space, and objects follow those curves. General relativity predicted light bending around the sun, confirmed in 1919, making Einstein a celebrity. It also showed time runs slower in stronger gravity, a fact your GPS relies on. Einstein's theories replaced Newton's mechanical universe with a dynamic, warped cosmos. But while Einstein reimagined the very large, another revolution was brewing in the world of the very small. The universe was about to get even stranger. Physics was on the brink of quantum weirdness. The next chapter would defy all common sense. Welcome to the quantum world. As Einstein redefined the cosmos, physicists probed the atom's mysteries. The ultraviolet catastrophe led Max Planck to propose that energy comes in discrete packets, quanta. Einstein used this idea to explain the photoelectric effect, showing light acts as both wave and particle. This wave-particle duality became central to quantum mechanics. In the 1920s, Bohr, Heisenberg, and Schrödinger built the quantum framework. Bohr's atom had electrons in quantized orbits. Heisenberg's uncertainty principle said you can't know both position and momentum exactly. Quantum mechanics was probabilistic, not deterministic. Nature is fundamentally fuzzy. Einstein disliked this, but experiments kept proving quantum theory right. Schrödinger's cat, alive and dead until observed, became a symbol of quantum strangeness. Quantum mechanics shattered classical intuition. The universe at its core was unpredictable and bizarre. Yet, this new physics explained the structure of atoms and the behavior of matter. The quantum revolution had begun. Quantum mechanics opened the atom, revealing a dense nucleus of protons and neutrons. But what held these like-charged protons together? The strong nuclear force, powerful but short-ranged, was the answer. The weak nuclear force explained certain radioactive decays. By the 1930s, 4 fundamental forces were known: gravity, electromagnetism, strong, and weak. Einstein's EXMC2 explained the missing mass in nuclei as binding energy. This immense energy could be unleashed by splitting, fission, or fusing fusion nuclei. The atomic age dawned with the Manhattan Project and the first nuclear bombs, forever changing history. Nuclear power also emerged, offering energy without fossil fuels. The study of the nucleus transformed science, technology, and geopolitics. The atom's secrets had been unlocked, with both promise and peril. Physics now looked deeper, searching for the universe's most fundamental ingredients. The quest for the building blocks of matter was on. After World War II, particle accelerators revealed a zoo of new particles: muons, pions, kaons, and more. Was there order in this chaos? Murray Gell-Mann proposed that protons, neutrons, and others were made of quarks. Quarks came in different flavors and colors, combining to form familiar particles. This quark model brought order to the particle zoo. Over decades, this became the standard model, the universe's recipe book. It lists 12 matter particles, quarks and leptons, and force-carrying bosons. But why do particles have mass? The Higgs field, proposed in the 1960s, gave the answer. Particles gain mass by interacting with this invisible field. The Higgs boson, discovered in 2012 at CERN, completed the Standard Model. The Standard Model is the most successful theory in science. Yet, it's not the whole story. Deeper mysteries remained, ones the Standard Model couldn't explain. The search for the universe's missing pieces continued. The Standard Model explains only 5% of the universe, ordinary matter. The rest is a mystery. About 27% is dark matter, invisible but detectable by its gravity. Vera Rubin's study of galaxy rotation revealed this hidden mass holding galaxies together. Even more mysterious is dark energy, making up 68% of the cosmos. In the 1990s, astronomers found the universe's expansion is accelerating, driven by this unknown force. Dark matter and dark energy are the biggest puzzles in physics today. We know they exist, but not what they are. The Standard Model can't explain them. Our understanding, though vast, is incomplete. The universe is mostly made of things we can't see or explain. These mysteries drive the next generation of discovery. The journey that began with the Greeks is far from over. The cosmos still holds secrets waiting to be revealed. Today, physics stands at a crossroads. We have 2 powerful theories: general relativity for the very large and the Standard Model for the very small. But they don't work together, especially in extreme places like black holes or the Big Bang. The quest for a unified theory, a quantum gravity, continues. String theory is a leading idea, picturing particles as tiny vibrating strings, but it remains untested. Meanwhile, physics shapes our world. Quantum mechanics powers computers and smartphones. Relativity keeps GPS accurate. Nuclear physics enables medical imaging. The pursuit of knowledge drives technology and innovation. Physics is a story of curiosity, from ancient Greece to today's labs. Big questions remain. What is dark matter? Dark energy? Are there other universes? The adventure of discovery continues, pushing the boundaries of what we know. As long as mysteries remain, physicists will keep searching. The universe is vast, and our journey is just beginning. The story of physics is far from over.